Good morning, everyone, and welcome to the IBM Qiskit Live Quantum Seminar Series. I'm delighted to be here today as your host, Zlatko Minev from IBM Quantum Research, and I'm also thrilled to see already so many of you tuned in to today's seminar, which is going to be quite special. I think this is a topic that's usually quite tricky, but Gianluigi Catelani, who is here and will join us in just a minute, is one of the few, if not the only person I know who can really break down what a quasiparticle is and how it interacts with superconducting qubits. And so I'm really excited to bring Gianluigi back here onto the stage in just a few minutes. But let's first begin by letting everybody tune in. And my favorite question, I can see many of you already anticipating it, which is, where's everybody tuning in from? But today I'm going to throw you a curveball, and I'm actually going to rather ask you to name any conferences or seminars or series or summer schools that you're really excited about and looking forward to in the next month or so. So you can reply in the comment chat box, which is on the right-hand side or right below here. And that's the same place where you can ask questions of Gianluigi Catelani during the talk, and I'll get those to Gianluigi as we go through it. And I'm glad to also see Frida and Madhavan and familiar faces here. I'm excited for QC40, which is happening next Thursday, the Physics of Computation conference, a 40-year anniversary of a very seminal conference itself. So looking forward to that. And also thank you to everyone for joining us from all across the globe here. I see people from India, New York, and all over. AQC 2021, I see that. This talk will stay recorded, and so you can go back and rewatch it, especially if you hit the subscribe button, but you can only ask questions live during the talk, which I think it's about time we get to. So with that, I think it's time we begin. I'm thrilled to roll out the latest episode of the IBM Qiskit Live Quantum Seminar Series, dedicated to you, the research and academic quantum communities. I'm your host, Zlatko Minev from IBM Quantum Research, and today I have the extreme pleasure and delight of hosting Gianluigi Catelani from the Jülich Research Center in Germany on quasiparticles and superconducting qubits, history and recent developments. Hello, Gianluigi. How are you today?
Hi, Zlatko.
It's good to see you. Yeah. Where are you tuning in from, Gianluigi?
Yeah, my office in Jülich, the research center.
Okay, wonderful. Before we pull up your slides, I'll give a very quick bio to Gianluigi. If you want to know about quasiparticles, Gianluigi is the man. He's been central to many of the big quasiparticle works in our field. And before getting very deep into that, he did his master's at Stony Brook University, then his Ph.D. at Columbia University of New York, from 2002 to 2005. Then he went on to do a postdoc at Cornell, Rutgers, and Yale before joining Jülich in 2012. And today we have the pleasure of having you, Gianluigi. So I think with that, I'll turn it over to you, and the stage is yours.
Thank you, Zlatko. So, before I begin, of course, let me, acknowledge a lot of collaboration during the years, especially, people at Yale, also RWTH, University in Aachen, nearby in Germany, then in France, both Saclay, Grenoble, and also people at MIT and in Karlsruhe. And unfortunately, I will not get to talk about all this, collaboration. I will focus on some of them. And this is going to be, as the title say, a kind of a historical review and with a bit of recent developments. But, for expert, let me just tell you, there won't be much new. This is mostly for people that are curious about these quasiparticle effects and they want to learn their history and what they're all about. So a brief outline of my talk. So I start with some motivation and background about, what are these quasiparticles and why do we care. I will give a very short prehistory, in a sense, from before 2010. And then I'll focus on measuring and controlling quasiparticles through vortices and traps. And towards the end, I will talk about more recent works about pair-breaking photons and also the effect of radiation. So what are these quasiparticles? Let me start, thinking about quasiparticle in bulk superconductor, not in superconducting qubit. And even before talking about superconductors, let me, remind you about a normal metal. And we can think of having, some kind of band structure where we fill all the states with electrons. up to the Fermi energy. But what I'm interested in is what are the excitation in a metal, and then you have to kind of excitation, electrons or holes. So electrons, if you can add an electron above the Fermi energy, or you can take an electron out from below the Fermi energy, and that's your hole. So these are the kind of excitations in metals, and those are the reason why even at very low temperature you can always generate these electron hole pairs, and that's why you have finite resistivity in the end because of also impurities. But that's why you can also always have even at very low temperature some finite resistivity in metals. Now in a superconductor, how do you make a superconductor? In principle, is that you want a piece of metal, but with some effective attraction between the electrons. So what happens is that these electrons, they pair up they form Cooper pairs, and these Cooper pairs, they can condense and form a condensate, so which is described by some essentially wave function or some order parameter, which has an amplitude and a phase. And the important point is that if we look at the excitation now, there's a gap for the excitation. So, and the reason is that, if I take one of these pairs and I want to create an excitation, I have to break this pair apart, and it takes some energy to do that. And for example, now if I look at what is left behind, let's say, here is like in the metal, I took out an electron, I got a hole. Now, if I do the same in a superconductor, what is left behind is not just a hole, but it's kind of a combined object, which is both a bit of a hole and an electron. And these are the quasiparticles. This excitation in superconductor, which are actually, they are a coherent superposition of electron holes, which mathematically is expressed by this so-called Bogolyub transformation, but is not important. The important point is that this is different, essentially, type of excitation that you have in a normal metal. And the other important things, of course, about a superconductor is that they can carry a DC current without any dissipation. And the reason they can do that is because of the condensate. But what about AC? Even in superconductors, there's usually some AC losses, but they're very small compared to normal metal. And the reason why they're small is because of this gap. Because, at finite temperature, if we populated this excitation, this level, these are still fermions, so there's a Fermi distribution. But because of the gap, there's only a very small population of excitation at higher energy up here. And because we have these very few quasiparticles, and those are the excitation that then absorb energy, and that's why even if there's some AC excitation, some AC current, there are small AC losses in a superconductor. So this is kind of well known since the beginning of superconductivity, and definitely also from the theory, from BCS theory, and soon after. In bulk superconductor, and if you want the question about qubit is what happens, what these low AC losses do to superconducting qubit. Why is that important? So to understand that, let me show you this plot that you may have seen, or similar one in previous talks also in this series of seminars, and it shows the lifetime of superconducting qubit versus the year in which they were introduced. And there are several types of superconducting qubits, Cooper pair, flux qubit, transmon, and so on. And in this talk, I will focus essentially on what are called Josephson junction-based qubit, not on this bosonic encoded qubit. And these Josephson junction are essentially, as far as I'm concerned, are two superconducting electrodes separated by an insulating layer. I will tell a bit more about it in a moment. And now, why looking at this plot with the lifetime is important? Because it takes a finite time to operate on qubits, right? To perform operations. So if you want to do a computation, you need to be able to control this qubit, to manipulate their state, and that takes a finite time, usually in the order of tens or hundreds of nanoseconds. So if you look at the very first few qubits, their lifetime was on the same order of the time it takes to operate on them. So it was basically hopeless to perform a computation with these qubits. So that's why you want to prolong their lifetime. And the other reason is that if they live long enough, of course, the lifetime is not going to be infinite, so there's going to still be error during the computation. But if they live long enough, this error can be detected and corrected. So through quantum error correction. And the question then is, how long is long enough? And there is some kind of threshold, which I'm showing here with this gray bar. Meaning that if your qubits live longer than this time here in the tens of microseconds, is at least in principle possible to do quantum error correction. And you see this kind of threshold was crossed over around 2012 with the 3D transmons. And in fact, just a couple of years later, there was this paper from Martinez group, that was telling about the superconducting circuits at this surface code threshold for fault tolerance, meaning that what they did here that was new compared to these dots here, these measurements were done essentially on single qubits, is that they were able to fabricate a chip with, if I remember correctly, 5 qubits, join them together and still maintain long enough coherence that it was above 3 threshold. So to show that at least in principle it's possible to do quantum error correction. Now there's a problem still here that if you're just above threshold, to have a logical corrected qubit of this kind, you will need to join together, I don't remember the exact numbers, but tens of thousands or hundreds of thousands of physical qubits. So, it's in principle possible, but in practice very hard to do. So what you want to do, in fact, then is to push this coherence times much farther. You want to be well above threshold, which means that maybe you can live in, 100 qubits or tens of physical qubits per logical qubit. So that's why we want to understand what is limiting this lifetime and how to improve them. So what can relax, for example? So yes.
Maybe a quick question, Gianluigi, from the first slide on. You brought up this nice point that quasiparticles from the condensate are very different from normal electron excitations. I guess for people who are a little bit newer to this, like what are some of the essential features that they should really remember and take away? Like what are the sort of key points to keep in mind there? If maybe you could highlight that for us.
Yeah. Again, so one of the main points
the differences between the two.
Yeah. Yeah, so again, so there are two differences. So one is that, this kind of quasiparticles, so if you think about the electron and holes, they have a very definite charge, for example, is positive, well, negative in the case of the electron and positive in the case of the hole. This quasiparticle, because they are this coherent superposition, for example, the charge is not well defined, but they can still interact, absorb energy, for example, and that's why they lead to relaxation. But the important point is that if you have a gap, then you have this very few of them, right? Because you don't have states between this red field band here and this white band there. And even at finite temperature, or for whatever reason, if you excite this quasiparticle, there's going to be very few of them because it needs a certain amount of energy that depends on this gap, on the order parameter of the superconductor. So that's why the reason why you want to use a superconductor and not a normal method to make a qubit, essentially, because of this gap, and then you won't have many of this excitation that can absorb the energy from the qubit. I'll be returning on that in a moment.
Okay, thank you.
Okay, so again, so the point is that we want to understand how to make this lifetime longer, or what is limiting this lifetime. And broadly speaking, one can classify this relaxation mechanism into 3 broad classes. So one is electromagnetic radiation, the other is dielectric losses, and the third one is quasiparticles. So let me tell you briefly more about each of them. So electromagnetic radiation, although these qubits, we can call them artificial atoms, but like natural atoms, they interact with lights, with photons. And we actually need this kind of interaction because it is useful, to drive or to manipulate the qubit and to read out their states. And this was also discussed in a previous risky talk by Alex Protescu. Then the second mechanism, dielectric losses, this is quite different from normal atoms, from natural atoms, is because we are fabricating these circuits on some substrate and using some fabrication recipe with some on some particular material and so on. And so, a lot of things can go wrong. There can be residue of this fabrication, or, the interface might not be perfect and so on. And this can also lead to losses. And, for example, Jürgen Liesefeld and Alexei Ustinov in Karlsruhe have worked a lot on this. And that I took this picture from one of their paper. And this was also discussed by Jonas Peilander also last year in another seminar. But this kind of losses, in a sense, are extrinsic to the qubit. They come from the outside wall. And this is what distinguishes them from quasiparticles, which are this, as I discussed, this intrinsic excitation in the superconductor. So I will not talk at all about this other mechanism. I will only focus on quasiparticles. And the question again is are these quasiparticles a limiting factor in qubits? And if they are there ways we can control them? So that's what will be the focus of the rest of the talk. Okay, so, but, just very briefly, although I will be focusing on qubits, this kind of question about losses and quasiparticle and so on, very important for many different kind of devices based on superconductor and Johnson junction, like connecting inductance detectors, or, for example, the voltage standard itself is defined through the Josephson effects, and there are also proposals to build current standard using superconductor or hybrid junction with superconducting normal metals. Josephson junction is used also to build amplifiers, and also there are several proposals for the quantum sensing, especially of magnetic field, using essentially flux qubits. So again, I will focus on qubits for quantum computation, but this issue is kind of more general. Okay, so let me give you a very brief kind of historical overview. If you remember, when I showed this plot about the lifetime of qubit, it started from 1999 with the first Cooper box experiment. But very soon people were worrying about quasiparticle again, because this was kind of an issue known from bulk superconductivity already. And so, for example, one of the first mention I found was from this abstract from the Applied Superconductivity Conference from 2002, in which they want to banish quasiparticle and why, and they explain why and how to do it, and especially they say that you need traps to reduce these effects, and I will return later in the talk about trapping quasiparticle. Then a year later, for example, again one of the same authors, John Martinez, in this abstract from March meeting 2003, he was also worried about quasiparticle heating, and how this could also be deleterious, and this extra energy essentially in your circuit. And then he was very, as always, the optimist, and he was saying that if you can control this heating, then we could construct kind of straightforwardly a 10 to 100 qubits quantum computer, which is where we are around now, which is almost 20 years later. Although, I have to say very briefly, I won't have time, I guess, to discuss this, that this quasiparticle heating, at least for like current qubits, is not really an issue, and we looked at it from a theory perspective in this paper from a couple of years ago. Then again, another year later, there was also other kind of experiment to measure this quasiparticle effect. This was done in a Cooper pair transistor, which is essentially a very similar design to the Cooper pair box, so to this first superconducting qubit. And essentially, so this is a circuit which is sensitive to some gate voltages. And what is important here is that there is an isolated superconducting island, which is then joined to the rest of the circuit through two junctions. And the point is that there are even and odd state, depend whether you have an extra electron or not into this island. Now, if we only have Cooper pair going through, this will not change the parity. So if it's even, it will stay even. If it's odd, it will stay odd. But if we have one electron or one quasiparticle tunneling through, it will change the parity of this of the circuit of the island. And what they show is that depending on how you design the circuit or the gap, so you can have two possibilities. In one case, you can design the circuit in a way that you're kind of favoring having these extra electrons or extra quasiparticles sitting there, or you can make it in a way that the gap is higher, so this quasiparticle will be kept out of the island. And then the periodicity in gate voltage changes quite abruptly. So this was a clear indication that, in this case, quasiparticles were there and kind of ruining this periodicity. And in this case, they were not there. This is known also as gap engineering, and it can also be used for qubit. And later on, there was a number of theory work, in particular by these people here, about this kind of design, especially for the Cooper pair box, up to until 2007, which is kind of where when the transmode was introduced. And I will discuss the transmode in a moment. So a few years later, that's where, I was not working on qubit back at that time, but a few years later, I got involved into this business. And the idea that, okay, this, for example, this series of work, they were focused on this particular design, in a sense, on the Cooper pair box. So, but can we come up with a general theory that we can apply to all qubits? So it kind of have a standard model of if you want, of quasiparticle effect in superconducting qubits. And so this kind of models, and this will be kind of the most theoretical part of my talk, it looks like this. So, a generic qubit, let's say, or a single junction qubit, comprises three elements, if you want: a superconducting loop, which is interrupted by a junction, and the junction itself, because it's two pieces of metal separated by an insulator, it also has some capacitance. So there are essentially, if you want to look at it in terms of a circuit, there are three elements. So a capacitor, an inductor, and this X is for the Jefferson junctions. And associated to these, three elements, there are three energy scales. So the charging energy, the inductive energy of the loop, and then the Josephson energy. And this knows about the tunneling of Cooper pairs to the junction. So then, if you want to model this quantum mechanically, you have to write down an Hamiltonian to describe this circuit, which also has three parts. And there's a part which is the qubit, the proper qubit Hamiltonian. And the point here is that, we can use the phase difference between the two sides of the junction as the degree of freedom where we can store and manipulate quantum information. So that's the main degree of freedom that we have. And again, there are three parts in this Hamiltonian, which they comes from these three elements I just discussed. And the most important one is the Josephson junction, which is this term here. And the reason is that if we don't have that, this circuit behaves like an LC oscillators. And now, while it is possible to build, to store information, quantum information also in LC oscillators, I will not discuss that. But if we do have these Josephson junctions, now this energy profile becomes more complicated, and now we can kind of distinguish two levels from the other levels and use those as our qubit. Although in practice, I mean, all these qubits usually come with many levels. Now, the second term is in this Hamiltonian is the one from the quasiparticles. And this kind of, they form a gas of excitation that live above this gap, as we discussed before. And okay, they're there, and at this level, they don't talk to the qubit. So, if this were all that there is in this model, then the qubit will live forever, even, in theory. But of course, there is a third term here, and this knows about quasiparticle tunneling. So the fact that the quasiparticle can also tunnel through the junction, and it has this form here. And you see that it depends both, this operator, they just tell us that you can kill a quasiparticle on the right side of the junction and create it on the left side. But the probability of the probability amplitude for this process, that it depends also on the phase difference across the junction, so on the qubit, on the state of the qubit, if you want. But the basic idea is very simple. So you have a quasiparticle, approaching the junctions. It can interact with the qubit. Let's say the qubit was in the excited state. And through this interaction, it can absorb the energy of the qubit, which decays, and the quasiparticle ends up to the other side at a higher energy. And now one can calculate these rates. I will skip maybe these details here. The important point is that one ends up with a formula, which is kind of very familiar form, I think, at least in this business, that, this transition rate between the state of the qubit is a product of two terms. So one is a matrix element, and this knows about this nonlinear interaction between the qubit and the quasiparticle, and the fact that it's nonlinear will be important later on. And then there's a part which is called a spectral density. This one knows just about the fact that the quasiparticle tunnels through and exchanging energy with the qubit. And at least in certain regimes, which are the ones which are relevant, it takes a relatively simple form. It depends on the frequency of the qubit, but also on the density of quasiparticle. And this is rather easy to understand, at least intuitively. It essentially tells us the more quasiparticle you have, the more they can attempt to tunnel to the junction, and the more they can absorb energy from the qubit. So the quicker the qubit will lose energy.
Quick question, Gianluigi. In this treatment, are we treating phi hat, var phi hat, as a wrapped variable or an unwrapped variable? Meaning, does it have infinite support? It's on a real line, or it's between 0 and 2 pi?
So that it depends. Essentially, it goes is hidden here into this matrix element, and it depends on the qubit design. So, for example, in a single junction transmon, you can treat this as a 2 pi periodic, or, well, there's some subtleties even there. It could be 4 pi periodic. But if you have, like a qubit with an inductor, this might be also on the real line. But in principle, so these are kind of subtle questions. So there's also discussion in the community about this point. So sometimes it is not maybe completely clear. People have different opinions on this point also. So I don't think I want to go into that right now.
Okay, we can save it for later. I'll state my opinion. I pretty strongly feel that it should be unwrapped, but we can save that for later.
Okay, yeah. Okay, but again, so the important point is that there are these two terms. So one, that is specific for each qubit, because I need to know what the initial and final state of the qubits are. It knows about this nonlinear interaction, kind of interaction. And then, it's kind of, this part is more or less the same for every qubit. It just knows of how many quasiparticles there are, essentially. So
one quick question. So in going from the upper golden rule to this sort of simplified rule, is this where we take some approximations, or so sort of what are some of the built-in assumptions in the model here?
Yeah, I skipped a bit on that. So one, simplifying assumption is that the typical energy of the quasiparticle, or the effective temperature, is small compared to the frequency of the qubit. So which essentially, it just tells us that the quasiparticle, they are all very close to the gap, they can absorb energy from the qubit but not give it back. So essentially, you have decay but not excitation, at least in these simplifying pictures. Then, if you go to thermal equilibrium and higher temperature, you can also take that into account and get more accurate expression. They get a bit more complex, but so it depends on the situation essentially.
I see.
But the point is that in practice we do expect to be in this regime expanding, because you cool down your freeze to extremely low temperature compared to the critical temperature. And actually, I mean, the expectation would be that there are 0 quasiparticles in your samples, but they're always there. So.
And there's all this talk of out of equilibrium quasiparticles, right? Is there any sort of progress on the theory on that on this end?
I'll discuss a little bit about that later.
Okay, right.
And also towards the end.
And maybe one quick question from the audience here: is there a simple intuition why the quasiparticle tunneling amplitude is modulated with sine phi over 2 here in the gamma? I guess, is there an intuitive way why you would reason that that's what the form should be?
Yeah. So.
It's a tricky question.
Yeah, so that's not really very intuitive. But if you go back to my initial introduction, right, I said that this quasiparticle are this coherent superposition of electron holes. Now, this superposition now it depends on the energy of the quasiparticle, the weights, how much it is a hole and how much it is an electron, and also on the phase difference. So that's where it enters essentially. And I'll discuss a bit more maybe in a second. I mean, there's no why is sine instead of cosine. The two I can kind of at least intuitively say that the phase difference is a property of the condensate of pairs, but here we are looking at the tunneling of a single electron or a single excitation. So that's why you have half and not the full phase. So that's kind of an hand-waving explanation of the factor of 2. And actually, if one is more careful, there are both sine and cosine that enters into this theory in a different way. Here I'm just showing kind of the main term, in this case, when the quasiparticles are cold. Yeah. So in these terms, I mean, it's not the most general one. So there's no really intuition in that sense, I would say.
Okay, thank you, Gianluigi.
Yeah, so, so can we kind of test this theory? And one of the, I will show you briefly some tests. One was done in the also using this transmon I mentioned before. And transmon is kind of a very simple qubit design in which you have 2 electrodes, a very big one even they can be, as you see from these pictures. And then there's a very small junction between the 2. And if we go back to this model here, Hamiltonian I showed you before, there's no loop, so we can drop this, and in principle there might be some dependence on some gate voltages, on some background charges, but in the transmon, because the charging energy is small compared to the Johnson energy, this is not important. And just to give you a picture again, let me look first at the opposite regime, the Cooper-Bock, which I also mentioned briefly before, and we saw already this kind of even and odd curves before, and essentially this is because the charging energy is the most relevant energy scale. So the energy depends a lot on whether you have, one extra, no extra electron, or one extra electron is this dashed line, or 2 extra electron is this other parabola, and so on. But the Johnson energy, because it accounts for the tunneling of pairs, it opens this gap between these parabolas, and these are the state you might want to use for a qubit. Now, so this turned out not to be a very good qubit for 2 reasons. So one is because you see this energy depends a lot on these gate voltages or background charges. So if there is charge noise, which kind of like move around these voltages, then it will change the frequency of the qubit a lot, the energy difference between the 2 states. And this is bad because it will lead to dephasing. And the other bad effect is that if a single electron tunnels through, it will go from one of these continuous lines, so an even state, let's say, to an odd state. And you have essentially lost your qubit. It's kind of disappeared. It's not there anymore. So that's not good. So what people did in 2007, when they introduced the transmon, was to think, okay, what happens if I increase the Johnson energy compared to the charging energy? And then you see that you open this gap farther and farther, and you push the even and odd state closer and closer together, and you end up with something like this, in which I still have exaggerated this energy difference between even and odd state. And this is good because now there's almost no dependence on this charge noise. And even if I have a quasiparticle transition, the worst case is that the qubit goes from the excited state to the ground state, but the qubit is still there, has the same frequency, and can still manipulate it. And also, in some other cases, actually, it doesn't even change the state. It changes its frequency a little bit, so there is a bit of dephasing, but this is not a big effect. So what was done then in this experiment here in 2011 was to measure the T1 time, so the decay time of this. This disappeared. Okay. So these green triangles are the T1 times, so the lifetime of the qubit, if you want, versus temperature. And you see there is kind of a flat part, and then it goes down very quickly. And the reason why it goes down very quickly is because your quasiparticles are being thermally excited. So this we can kind of predict from theory, and it matches very well with this dashed line. That's the theory. And the other part of this line, the one at low temperature, one could assume that for some reason, which we don't know, there are some non-equilibrium quasiparticles with their normalized density here is very small. So this is like the fraction of broken Cooper pairs. So you see that to explain this flat part at low temperature, it's enough to have something that breaks less than one Cooper pair out of a million, and it could explain this T1 time there. The question is why, if this were like thermal excitation, this would go on, like this, it would be exponentially longer, but that's not what happens in practice. This, again, I mentioned this kind of measurements in transmon qubits, but, very soon they were also, seen in other design qubits, like flux qubit, for example, and again, same kind of fits. This data from a phase qubit, and this fit is not with the quasiparticle theory. This is actually from the spin boson model. The fit with the quasiparticle theory looks like that. And if you are actually observe very carefully this, you'll see that the lifetime here is much shorter. And this is actually because this is a paper from 2007. And that's why the fit was done with the spin boson model. There was no theory, well-developed theory about quasiparticle back then. But it's remarkable that despite this short lifetime, they could measure this very carefully, although they didn't have an explanation for it. Another effect also that I didn't discuss, but the theory predicts, is also that the qubits will change its frequency a little bit when you add quasiparticle. And in the same paper I just discussed about the 3D transmon, this frequency shift was measured, and now the theory curve is with no free parameters whatsoever, and there's reasonably good agreement between theory experiments. And around the same time, there was also another experiment with a phase qubits. And here, actually, what was done was injection of non-equilibrium quasiparticles. So these quasiparticles were added on purpose. Now, you don't know, how many of them are added, so you can't predict how much T1 or the relaxation rate will change, or how much the frequency will change. But we know they are related to each other because they change with the density of quasiparticle, and this linear relationship was found. So this is kind of all tests of this theory. Soon after it was formulated, there were these tests, so everything works nicely. Another, very important step was actually looking back at this, at the fact that this quasiparticle have this coherent superposition, which we were discussing just a short time ago. And why is that? So this goes back actually to what was known in the field as the Crossfire Problem. So let me explain briefly what this problem was. Essentially, what people were looking at, this was already in the 60s and 70s, was not a qubit, but just the response, if you want, the admittance of a junction, and especially the real part, so the losses again. That is the same kind of effects that we are worried about in qubits. And the fact that this quasiparticle are a superposition of electrons and holes, it means that if they tunnel as an electron, they pick up a certain phase. If they tunnel as an hole, they pick up the opposite phase. So quantum mechanically, there can be an interference effect. And so this loss is proportional to 1 plus cos phi. An important point here is that now if this phase different, if I can tune it to pi, this will go to 0. So it's very important. We can kind of suppress the losses by carefully arranging the phase difference across the junction. Now, why was this a problem? Was that because, generalizing this expression, we can put some prefactor epsilon here. And again, the theory was that going to low temperature, this factor should be 1. But the experiments done in the 70s, essentially at low frequency, this was all over the place. It was anywhere between -1 and +1. So there was this disagreement, unresolved tension between theory and experiment. That's why it was called the Crossfire Problem. Mm-hmm. Looks like you have a question.
Yes. If you don't, it's from the previous slide, but I just caught it from Christian Anderson. Good to see you. Are those curves really indication of non-equilibrium quasiparticles? Don't these measurements just say that below a certain temperature there is some other loss mechanism like TLS, etc., that limits T1?
Now, that's a good question. That's why, in the slide before, there was a question mark about this non-equilibrium quasiparticle. Right? So that's a possible interpretation, but it's not the only one. Indeed, it could be something else. And in fact, there's good evidence that at least in certain cases is something else. But I will get to that point in a few slides. So I will come back to this. So if I don't answer the question, you can ask again later.
Yeah, type it in at the end in the chat at the end again. Okay, thank you.
Okay, so again, there was this tension between the experiments. So can we look at it using qubits, try to resolve this question? So there are flux tunable qubits, and one example is the Flaxonium that there was also discussed very recently by Vlad Marcharian a few weeks back in another talk here. And the Flaxonium is made like this, so there is a small junction, then a series of junctions. But in practice, you can just think about this array of junctions as an inductor. And the point here is that now we can tune the properties, for example, like the frequency of this qubit by applying a magnetic flux to this loop. And so if there's no flux, you have some high frequency, then as you increase the magnetic flux, the frequency goes down. And usually you want to be down here, what is called a sweet spot, because then you're not very sensitive to flux noise, so the changing flux through the loop. And when you're down here to this sweet spot, the energy diagram looks like this. So it looks like a double well potential, and then we have this level splitting, and these are the state we can use as a qubit. So how does this relate to this Crossfire problem? Again, before, in the case just of a junction, this was the interference from electron and holes, but there's a similar effect here. If we calculate the relaxation rate for this qubit when it's close to this half-flux quantum to be tuned to this lowest frequency point. And the point is that, again, if this relaxation rate goes to zero, if there is exactly a flux quantum through the loop, and the reason for that is really because the wave function, one is symmetric, the other anti-symmetric, but then there is this sun phi over 2 that I mentioned. It would come back here to be important, because if this were some different function, or like, for example, usually an environment is supposed to linearly couple to your system, at least in a good approximation, but then this cancellation wouldn't be there. So the fact that this is really this sin phi over 2 is quite important. And again, it goes back to this interference effect. So if you can see this effect in qubits, it kind of tells us that this theory prediction was correct. So this T1 time was measured as a function of flux, and the total theory prediction, as I mentioned, there are kind of 3 contributions. This Purcell effect actually is from this photon losses, so electromagnetic radiation. Then this green line is dielectric losses, and then this red line is quasiparticle. And you see, as you tune the frequency down with the flux, this qubit started to be dominated by quasiparticle. And if we zoom in near this region of flux quantum, although there are fluctuations, and this is due to the fact that sometimes you have more quasiparticles, sometimes you have less, there is a well-defined peak that follows the prediction from the theory. So this kind of, again, solve this Crossfire problem in the sense that it really verified that there is this interference effect, and with the sign expected from theory. Good. So now, so we understand exactly after these experiments, we are pretty sure we understand what the quasiparticle do to the qubit. And the next step is say, let's try to learn something more about the quasiparticle, and in particular about their dynamics. And the point here is that, again, we know now that the relaxation rate of the qubit is proportional to the density of quasiparticle. So can we monitor the density over time, so how it changes over time? So there is a phenomenological description or expectation of how this density should change in time, and there are 3 effects. So one is recombination, and as we discussed at the beginning, so these quasiparticles, they come from broken Cooper pairs, but the opposite effect is also possible. So you can take 2 quasiparticles, they can recombine again into a Cooper pair. So then the density will go down, right? And it will go down proportional to the square of the density, because again, you need to have 2 quasiparticles to meet together to join into a Cooper pair. And then when you have subtrapping, so again, the qubit is sensitive to the quasiparticle that can tunnel through the junction. So if for some reason they get trapped somewhere else far away from the junction, then they will get stuck there. They will not move anymore. They will not make it through the junction. So this density of the quasiparticles that can affect the qubit will go down. And then again, we know that for some reason they're there, even though, at very low temperature they shouldn't be, so something is generating them. So this is kind of phenomenological description. Now, can we see this phenomenologically in qubits? So the idea there was to take one of these transmon qubits, this large one, and in some way flood them with quasiparticle, and then start measuring the decay rate right after this injection of quasiparticle, this flooding. So very soon after, you see this rate is very high. But if you wait a bit, then this rate will go down, and at some point, we will reach back to this background value. And now I can try to fit this curve with this model in several ways. For example, I can say that there is recombination and no trapping, and then I will get this line, which clearly doesn't fit very well. Or I can do the opposite. I can say there's only some trapping, but no recombination. I will get the red dotted line, or I can include both and then get the thin black line. But essentially, you see the red dotted and thin black are almost indistinguishable, which means that, essentially here, what was going on, it was trapping of quasiparticle. So something is trapping the quasiparticle away from the junction. And now, this experiment was repeated with a kind of slightly different design qubit. I mean, it's the same material, same fabrication process, and so on. It's just, much longer and skinnier. And now what happens is kind of the opposite. If you try to fit the data, this time dynamics only, describe it only with trapping is not so good. But is almost is essentially here you're dominated by the combination because there's very little difference between the black and green line. So one wonders why is that, and to try to find an explanation, you try to change something else in the system. One thing that you can change is to cool this qubit now, this skinny qubit, into a magnetic field. And then what happens, if the magnetic field is very small, nothing much happens. But then as you increase the field, the recovery of the qubit is faster and faster. So this quasiparticle, actually, what happens is that what changes is the trapping rate. So you can extract the trapping rate from these curves, and the trapping gets faster and faster. And even more interesting, if you zoom in down to this region, that small field, it doesn't grow continuously, but it grows in steps. And the explanation is that when you cool your device in fields, you create superconducting vortices, so region in which the order parameter goes to 0, and they can trap this quasiparticle. So the higher the field, the more vortices you have in your qubit, and the faster they can suck up the quasiparticle that you injected into the system, so the faster the recovery is. And in fact, it is not only the recovery that goes faster, even the T1 time, for example, these red squares, increases a little bit because you keep the average number of quasiparticles lower when you can trap them away. Although at some point things get worse because also the vortex themselves, they're kind of like little pieces of normal metal that can move around, so they lead to dissipation. And moreover, also, the trapping of vortices in the circuit kind of stochastic. You see at the same field, sometimes you have 0 vortices, 1 vortice, or 1 or 2, and so on. So it's not a very controllable way to trap quasiparticle. But that led to the idea to go back to this trapping that I mentioned at the very beginning in this historical overview. And one way to do trapping is just to add a little bit of a normal metal on top of the superconductor. So here the yellow is aluminum, is the superconductor, and the orange is just copper. And it sits on top of the superconductor, and they're separated by a very thin insulating layer again. And the idea here is that if I have a quasiparticle in my superconductor, when it gets close to this to the normal metal under there, it can tunnel into the normal metal. And then two things can happen. So one thing, which is what we want, is that the quasiparticle relaxes inside the normal metal, it loses energy. And now because of the gap, if it's down here, now there are no excitation, it cannot go back. So it's trapped away from the junction, it doesn't hurt the qubit anymore. But also what can happen, of course, is that the quasiparticle tunnels back. And that's bad because now we can also go towards the junction. So what we want is that this relaxation rate, in some sense, has to be fast compared to the escape rate back into the superconductor. And then this trapping can work. Now there's a problem because this density, you see, I plotted here the number of states that there are in the superconductor. And essentially, the fact that we remove this state to create this gap for the excitation, they all get piled up over here near the gap edge. So there are a lot of states here. This makes very easy for the quasiparticle to escape. Now, of course, this quasiparticle, and in fact, has a distribution of energy. So on average, this escape rate is finite. And one can then derive some kind of condition on when the rate is fast or small. And then it will depend also on the temperature of the quasiparticle, so their typical energy above the gap. Now, if this relaxation rate is fast again, then the effective trapping rate is really the time it takes to get into the normal metal, the rate for that, because then the excitation relaxes quickly. If we are in the other regime, that relaxation is low, then the effective trapping rate is not only the relaxation rate, but is further suppressed by this ratio of temperature to gap, because it knows that the fact that it can go back into the normal metal. So this was also checked in experiments, and again, looking at the dynamics now in the presence of traps. So on top of these three terms I described above, recombination, trapping, and generation, we can also have to account about the diffusion of quasiparticles and the trapping of the trap. Now, diffusion, because now the system is not homogeneous anymore, and this has some particular geometry, so I have to take that into account. And the trap that is also in some limited region of the circuit. Now, it turns out that when I add the trap, I can basically forget about what I measured before is the main effect. And then, naively, this term that is, proportional to minus the density itself will give me some exponential decay rate of the quasiparticle density, although the actual rate and the density profile, it depends also on the geometry and so on. And in fact, there is kind of a typical length or a minimal length that tells us when the trap is strong, in the sense that it will be very effective at trapping the quasiparticle, and it depends on this balance between diffusion, the geometry, so the size of the qubit tail, and this effective trapping rate. So what was done in the experiment was to essentially fabricate qubits with the same design, so the same geometry, same length, but different trap size, and to measure this decay rate of the density as a function of this different trap size. And then you can see that there is this kind of crossover between a weak trap, in which the trap is small, so as you make it bigger, the trapping rate grows with the size of the trap. But then at some point, it's big enough that that essentially what limits the effectiveness is the time it takes for the quasiparticle to reach the trap, so the diffusion inside the system. And this was measured at 2 temperature, and it was, the result was that this trapping rate depends on the temperature, which is what we expect if the relaxation is low, which is a bit unfortunate, because it would, of course, be better if the materials were such that we had fast relaxation, but that's what it is. And there's probably not much to play around in terms of material here, in terms of improving this relaxation rate. So what we looked at, although I won't have time to discuss, is kind of how to optimize this trap position and side. What happens, this is a piece of normal metal, so one may worry also if you add loss instead of helping the qubit, and that one way actually to avoid this potential problem is to actually use as another superconductor with a smaller gap. So we discussed this, but I won't have time to go into any detail here. What I want to move on instead is some more recent experiments that, going back to this transmon, and if you remember, we discussed this state of having different parities, right? In practice, the qubit is not really, there are 2 logical states, but there are 4 physical states. And for each logical state, there are 2 states with different parities. Now, as I mentioned, usually one wants to go into a regime in which you can't really distinguish the different parities. But if you kind of move away a bit from that regime and move back towards being more like a Cooper box, you can still distinguish the state, and then it's possible to measure all the transition rate between, and check whether the parity has changed or not. So these red lines are quasiparticle-induced transition because the parity is changing. So and this green arrow, for example, is a relaxation which is not due to quasiparticles. So what was done in this experiment at Yale in 2018 was to try and measure all these transition rates. So they were able to do it. And in particular, what it turned out, for example, is that the main relaxation mechanism is not from quasiparticles. So it's one of these vertical arrows. But now if we focus actually on the relaxation due to quasiparticles, which goes back to this question whether the quasiparticle, the low temperature effect of the quasiparticle might be dominant. So it's not dominant here because this rate is faster. But if we focus still on this transition, which we are sure is due to quasiparticle, and we plot it again as a function of temperature, we kind of find the same behavior. So there's a thermal part down here, and then this kind of a flat part at low temperature. which again, so it looks maybe they're not dominant, but it looks like there are still non-equilibrium quasiparticles there. Now, as I said, they could also measure all these other transition rates, between the different parity states and also the excitation rate and so on. And what they found is something like this. Again, they also vary with temperature in a similar way. This kind of flat low temperature, then it grows with increasing temperature. And what is kind of bad is that this transition rate, as I mentioned at the beginning, they might be responsible for pure dephasing. So in principle, we might want to decrease this transition too. And here are the order of 100 microseconds, which we know if we want to push this coherence times much farther, this is not good. But the very strange results, which was kind of the reason for this title of having hot non-equilibrium quasiparticle, was this fact that if you compare the excitation rate due to quasiparticle to the relaxation rate, they're kind of the same, order 1. And if you assume, if you want to give a temperature or an effective temperature to quasiparticle, this means that the quasiparticle are very hot, because they can, at the same rate, they can either absorb energy from the qubit or give energy to the qubit. And this is only possible if their effective temperature is very high. So this is kind of strange, because again, this as usually you operate qubits down here at very low temperature, and I would expect the effective temperature of the quasiparticle to be very small. So how can we explain that? Is there any other explanation? So to get there, let me go back to this quasiparticle, this tunneling Hamiltonian that I discussed at the very beginning. And there was this question of about having this sine versus cosine and so on. And as I mentioned, I kind of was focusing at the beginning only on this main term, which is responsible for single quasiparticle tunneling. Again, so quasiparticle is destroyed on the right side and created on the left side, for example, or vice versa. But there's another term which comes from now with the cosine, and now this accounts for two quasiparticles be either created or destroyed at the same time from on the two sides of the junction. Now, the reason why I kind of neglected this term was that usually this is responsible for the tunneling essentially of Cooper pairs of excitation, if you want. So it gives us these Joseph energy terms that I put there, this EJ cos phi that I put in my qubit Hamiltonian. But there cannot be qubit-induced transition, because again, you need to give them enough energy above twice the gap, so to have this kind of transition, so to break a Cooper pair, to have this contribution here. And because the qubit, of course, frequency is well below this 2 delta, this cannot happen. So essentially, the main contribution from this term is giving you the Joseph energy terms in the qubit. There's some effect also in this frequency shift that I discussed before, but it doesn't give relaxation in usual terms. Now, and again, the reason why it does not give a relaxation, because the qubit has not enough energy to break pairs. So now one can say, okay, but there's not only the qubit, right? The qubit is not perfectly isolated. What if there are some high energy photons around, that they reach into your circuit, because you have cables, you need to be able to talk to this qubit, to manipulate them, write their state, and so on. So they're not perfectly isolated. So maybe sometimes some photons came in with with enough energy to break pairs. Then we can kind of include that effect by adding some phase fluctuation, essentially, due to these extra photons on top of the phase difference that is my qubit mode. And for the expert, you can relate the strength of this fluctuation to the coupling strength to the cavity in which you put your qubit. But the main point is that now we can kind of do a next to leading order calculation. So we can do a perturbative calculation in the tunneling and also in the strength of this weak coupling to this additional photons. And again, you get an answer for this relaxation rate or these transition rates, which is a very similar form as the one I discussed before. So there is some matrix element, and they can come both with the sine or the cosine, and some spectral density term. Now, this is, again, next to leading order in the term that there is a tunneling amplitude through the Joseph energy here, and the fluctuation or the coupling strength to these photons there. And here, this was the terms we discussed before was only kind of a leading order, because this was only perturbation in tunneling. But what was small here was that this was proportional to density of quasiparticle. There was a small factor due to the density of quasiparticle, which is not here, because this spectral density can be found at even a perfectly zero temperature. Because if you have enough energy to break Cooper pair, you don't need quasiparticle already be there to tunnel. You create new quasiparticle with this effect. So can this explain the data? So let me go back to this experiment. And again, I mentioned that the expectation, if you have only single quasiparticle tunneling, and now my slide seems to be stuck. Okay, so if you have only single quasiparticle tunneling, the expectation is that the excitation rate due to quasiparticle is just much smaller than the relaxation rate, but this is not what was seen in the experimental low temperature. On the other hand, if you have this photoassistant, this tunneling, so the effect that these extra photons coming in from the outside world can help breaking Cooper pair, then actually the excitation relaxation rate can be very similar to each other. And in fact, you can try and fit the data by summing both effects. So both having this photon-assisted tunneling, having these photons that break pairs, and also this thermally excited quasiparticle, and then you can kind of fit at least 3 out of these 4 rates reasonably well. And as a further check, the same device was measured again, but by improving the shielding and the filtering, so by isolating the device much more. So this kind of parity change rate, so that here was 100 microsecond time scale, went up to 6 milliseconds. And now, this is kind of also, there's very recently, one of the questions is how these photons make it to the qubit. And this was discussed also a couple of weeks ago by Rob McDermott, how these antenna modes that are in the qubits can couple to these photons. So I invite you to look back at this talk and this paper. And this brings me towards the very end of my talk, which is another mechanism. So I just discussed these pair-breaking photons. That's one way in which quasiparticle can be generated. Another way is that is shown briefly here. So is some radiation. So let me try to explain. So what was measured in this experiment in the group of Jan Popp and Karlsruhe was what they were measuring actually or monitoring were superconducting resonators, not qubit, but again the physics is very similar. And so what they're monitoring here was, over a relatively long time of tens of minutes, was the frequency of these resonators. And this kind of blip that you see, or you can also see on this side, it was the frequency versus time. So, you see there's some small fluctuation and then a relatively big change in frequency, and then over a couple of seconds it recovers. So the idea here is that what happens is that something deposits some energy, something happens, it dumps energy into the substrate or into your chip. This energy then ends up breaking Cooper pairs in the resonators. This shows up in the change of frequency. This is very similar to the frequency shift I discussed for qubits. And then, after some time, these quasiparticles, they go away and your frequency recovers. So as a further test, what was done in a later experiment was to add some extra material, extra aluminum, near to these resonators, and they can act as kind of absorbers. So they can absorb this extra energy. And now you see, without this absorber, you see this kind of effects, a lot of like big jumps and also a lot of small jumps. But if you add this kind of extra absorber, the signal is much cleaner and there are many less events. So it kind of confirms also this idea that something is depositing this energy. So now what this something is, yes?
Yeah, quick. Oh, right. These were granular aluminum. Okay, I was wondering why the sensitivity was so high. I was trying to remember why the delta F was, half a megahertz there, but it's these are extra high sensitivity.
Yeah, these are high inductance. These are like built on purpose to be very sensitive to these effects, so it makes it easier to measure them.
Oh, okay, right.
But yeah, so I won't go into much detail because actually this was one of the first Qiskit seminar back in May of 2020. So, this experiment and also further experiments were discussed. So I invite you to read this paper, which should hopefully appear soon in publication. And also a previous experiment in the MIT group, looking, what can cause this kind of quasi-particle generating event, whether it's ambient radioactivity, cosmic, and so on. Also, Rob McDermott, a couple of weeks ago, he discusses also similar effect that can also lead to charge noise in these circuits. So again, I invite you to look at that talk and these papers. And there was also a paper by John Martinez and the Google group discussing these effects very recently.
I have to also commend you on noting, that we've covered most of these papers here.
Yeah, so this is kind, is a bit out of sequence. So I would say, people, if you haven't seen these talks, now hopefully you have some kind of background information to enjoy them better. Or if you have seen them and you have some doubts, maybe now it's time to look at them again.
That's great. Thank you for noting that.
Okay, so that's basically the end of my talk. So let me just bring up, my brief summary. So I told you, a bit about this theory of qubit relaxation and other effects. I didn't talk much about the phasing, but I talked a bit about this particle switch and frequency shift into quasi-particle. I know it's valid both for in and out of equilibrium quasi-particle. There are various tests, various experiments. In particular, I like a lot this quasi-particle interference affecting the Flaxonium. I discuss a bit quasi-particle dynamics in present vortices or how to modify it with normal metal traps I didn't get to discuss this pumping, maybe another time. I got to discuss about these pair-breaking photons and introduced to radiation effects. And that's it.
Okay. Thank you, Gianluigi. Perfect timing. We're right on the dot here. Folks, please post any final questions for Gianluigi you have in the comment chat box on YouTube, and I'll get those up to him now. I know we had a few questions that were buckled up. There was the one from Christian on is this really indication of non-equilibrium quasiparticles, or could there be some other loss? And there's kind of a follow-up question to that. Oh, by the way, I see Kyle Cerniak is here, so thought I'd say hi. And there was a question also from Matthew Beck on the theory predicts a linear relationship between the change in the qubit frequency and the qubit relaxation rate from the quasiparticles. And this has been seen in some of the experiments from Yale and Madison and others. Although I think Matthew says, the scaling was a little bit different from that. And he was wondering what your thoughts are on that, if you had any comments.
I guess this goes back to one of these slides, so this experiment on this phase qubit. Yeah, so again, the idea is that, so the proportion that both the frequency and the relaxation rate, at least in some regime, they should be proportional to the density of quasiparticles. So that's why then, even though if you don't know the exact density, so in thermal equilibrium we can calculate the density. But these were quasiparticle injections, so we don't know how many of them. And now my presentation crashed, so sorry.
Yes, we've been teleported to a beautiful island.
Yeah.
That's okay.
So again, the idea was that even though you don't know the density itself, if you are in some regime in which both the frequency shift and the relaxation are linearly proportional to the density, then you can just plot one towards the other, and then check for this that they are both proportional to each other. So that was the idea, but this is not always true. It depends a bit on the detail of the qubits, and also at some point, if you add a lot of quasiparticles, then the relationship are not linear anymore. Even in this thermal equilibrium fact, I showed this very simple formula, which was some kind of square root of T over delta and some exponential, but this is valid only at very low temperature. Then there are some more complicated formula that you can work out, which actually you need to do an accurate fit of the experiments. So it depends a bit on the regime, but overall, I would say there was also some, of course, in an experiment you also have some spread due to some error bars essentially. I would say that overall it was already a good check about the non-equilibrium quasiparticles for sure. And actually, even in the later experiment with the quasiparticle injection and the vortices, I didn't show that, but this was checked again. And there was some, it was okay within a factor of 2. So again, why exactly that's the reason is not clear. But again, a factor of 2 is not too bad.
Yeah, condensed matter is tricky and tough. There are a couple of questions centered around, given all this very nice theory and nice fits to the experiment, whether or not within a factor of 2, do you have suggestions for experimentalists for designing new qubits?
Yeah, that's a tricky question, right? And that's what also I think a lot of people are working on. So making concrete suggestion, I'm not really, if I'm giving some other people work away or something, so I'm not sure what can I say. So definitely there is space for optimization. So let me be kind of very general and in several aspects. So one is the design of, if you want, of the qubit environment itself, right? So for example, if you have, like this 3D transmon, usually they're kind of well isolated, and the idea there was to diminish the role of the two-level system, because you have a lot of electric fields spreads around in the vacuum, essentially around the qubit. So it's not very sensitive to the two-level system, right? So that's one design, but then you might be more sensitive to other things, right? So maybe to these quasiparticles, or maybe if you have flux tunable qubit and you make them too big, they're more sensitive to flux noise. So then also, these qubits, and maybe let me pull this up, are relatively big, right? Like a millimeter. So maybe if you want to scale up, that's not a good design choice. So maybe, and in fact, like these XMON qubits, for example, that Google use, and even the Transmont IBM, they're a bit smaller than this. You want to maybe stay in the 100 of micron. So maybe then you get more sensitive to TLSs. So then you might want to think about material, changing material, change fabrication process. And I know IBM also is worrying a lot recently about reproducibility, right? I mean, because every time you're thinking you're fabricating always the same junction, but in fact they're all a little bit different. That is not helpful in scaling up because you want to have a good control on the chip you're preparing. So there's definitely a lot of research that can be done in material science, which is not really in my area, so I'm not probably the right person to ask about this. In terms of circuit design, I think there's also room there for improvement. Now, there's, for example, the kind of this flux tunable qubit, like flux qubits, Flaxonium, and so on. Especially the flux qubit for several years was kind of neglected because of this flux noise issue. But then, a few years back, it was shown that with this 3D design, for example, this coherence time could be improved and made reproducible. This was studied both in Saclay and then at MIT and so on. So there's now interest again in having these qubits with different kind of circuit and different properties. And for example, this Flaxonium, there was, again, very recently, this was from Vlad Manacharian, in which they show very long coherence times, both T1 and T2, I think in the millisecond range, if I remember correctly. Although these are very low frequency qubit, so there are other issues there in how fast you can manipulate them and so on, but they have schemes for that too. So I think, it's kind of an open question. For several years, a lot of people focused on Transmont, but, and it's a very good qubit, right? And it's robust, it's relatively easy to fabricate, maybe compared to these arrays with hundreds of junctions. So I'm not an expert, so maybe you can tell more on that, how hard it is. But again, I think that there's still work to do. I mean, it's not a closed question.
Yeah, I think you anticipated and somewhat covered the next question, which was from the audience on, do you think a material platform change could help avoid quasiparticles going forward? I think you touched on that probably there's a lot of work to do there. Maybe what we can...
Yeah. Because also people, for example, have done the capacitors with different materials, right? Usually it's like niobium, titanium nitride, for example, of this kind of higher gap superconductors, which is a bit counterintuitive because you could push the quasiparticle toward the junction, because on the other hand the junction are always made with aluminum. On the other hand, aluminum is also very good compared to these other materials, because essentially it turns out that almost every impurity you put in it turns out to be well screened and non-magnetic. Because then if you have magnetic impurities, you have this, instead of having this well-defined gap for the excitation, you get this broadening, you get a lot of subgroup state and so on. And that's the issue with this kind of material. That's why, there were qubits made with niobium, oxidized, proximitized aluminum niobium junctions. But these were very short lifetime. I think it just in a few nanosecond or range, if I remember correctly. So they were completely abandoned, for example.
Yeah. Sorry, go on.
Yeah, no.
I was going to say, Gianluigi, you must be clairvoyant. You keep anticipating every question I'm going to ask you. The next question was about subgap states, and you just started touching on that. Yeah. It was a general question about your opinion on subgap states, I suppose their importance and so forth from Karthik.
Yeah, so maybe let me pull up one of these extra slides and tell why you don't want subgap state in general, if my slides collaborate. So actually, we did worry about these subgap states in the case of junction, of having this trap, right? So, because the problem is that when you have this normal state, they kind of induce this subgap state. So I'm showing here this. So this line, let me maybe see if I can make it a bit bigger, if it works. But the point is that the normal metal essentially broaden the density of state and induce some subgap states. Okay. Mm-hmm. And so the qubit frequency is somewhere down here, where there is still is very small but finite density of this subgap state. Now, this because they're at lower frequency, they're easier to populate. So if you have this kind of long tail, even though they're small density, they can be dangerous. Now, in the case of a normal trap, the things to do is just to make the trap far away from the junction, because as you move farther away, this density of subgas state goes down exponentially fast. So with the trap, you can find kind of an optimal distance. If you get too close, it gets bad because of the subgas state. If you move it farther away, it's good because it depresses the density of the quasiparticle at the junction. So there's kind of an optimal trade-off. But the length scale is very different, because this length scale here for being bad for the qubit is the coherence length, which is typically in the hundreds of nanometers, sorry. And the trapping length is much longer, like tens of or hundreds of microns. So there's a good separation of scale. So it doesn't hurt you much if you move a bit farther away. It hurts you a lot if you're, across this point, this optimal point. So in principle, I mean, the subgas state can be very bad. Now, I have to be clear though that in general, what is measured in material like niobium, it is broadening up here. It's not clear if it continues down there. So people have been measuring this, and they can see there is a tail. It's not clear how much the tail, continues down, whether it extends to the qubit frequency or not. If it does, it's bad.
And this is very interesting. And could you comment on what subgap states, though? Let's say you have no normal metal around, but maybe there's other impurities or, I don't know, boundary effects or grains or who knows what. What happens with subgap states there? Do you think we see those? Could you have maybe a very low density, like an individual subgap, but it's a very strong thing, and then that couples to your qubit and does something bad? Or
yes. So now, so this subgap state, again, usually they're present in this, I mentioned, like niobium alloys. These are very disordered material in general. So what is known to happen also from theory is that these subgas states are in general present, if you have no magnetic impurities at least, close to the gap. So you get some broadening, they're kind of live here. So that's why people can clearly see this kind of tail in the density of states. But then they kind of stop here. Although there was some recent work, I don't remember, I think from the UK group, and also probably with resonators, and measuring some niobium alloy, which essentially they said, okay, we measure some effects in these resonators. They look like two-level system, but what they think they actually have are this localized subgap state, but close to the gap. And then they form kind of traps for quasiparticle that they could look also as two-level system. So this is also one possibility. Now, if you have magnetic impurities, that's in general much worse, because depending on the property of this impurity, they could be anywhere. They could also form band of state actually more extent. So if you have, but that needs kind of a high concentration. So as far as I know, this was looked at least from theory, also from Leonard Grasman with other collaborators, and the indication is that this is probably not the case. That magnetic impurities don't probably create; they're not dangerous. And again, the experimental evidence in aluminum is that for some reason all the impurities are essentially not magnetic, so they will not be dangerous for aluminum. But for other materials, they could be.
I see. That's very interesting. I think maybe final, I'm not sure if this is a question or a comment. This is probably the last one since we're coming on the 15 mark here, but I guess I'll bring it up. It's close to my heart. Frida noted that Qiskit metal needs a quasiparticle library. Since you and I talked about Qiskit metal before this, in quantum device design, I thought, yeah, what's your opinion on that?
Yeah, so I have to say I'm not either a numerical or computer person much. I have to tell you that essentially most of what you've seen, is kind of pen and paper calculations, right? Then of course, when you want to compare to data at some point, and when you work with real parameters and so on, sometimes you can't use these approximate formulas. For example, as I mentioned, like this temperature dependence, one has to be a bit more careful. And from theory, you get like some complicated Bessel function and so on. So you can't fit that by hand, right? I think again, I'm not an expert in this kind of approaches, but if it's possible to include them, of course, it would be useful. And the reason is that even though now this qubit, I would say, my opinion is that most of this, especially transmon qubit, with coherence times on the tens of microsecond, they're most likely limited by TLSs, some defects in the junction or the surface. So it's not quasiparticle. But again, the need, if you don't want to build achieve with 100,000, I don't know, tens of thousands of qubits just to have one logical qubit, which is you don't want to do that, right? So you want to push this coherence time much higher. Then if we can solve this issue with the with the TLSs, you will soon run into this quasiparticle problem, because all the indication from all these experiments is that if you're not very careful, you'll run into problems, if not in the hundreds of microseconds, definitely in the millisecond range, which is where you want to go, a few milliseconds probably. At least what people more expert than me in quantum error correction say. So it's definitely, in the circuit design, it will, maybe it's not needed right now, but if you want to continue, it will be needed.
Wonderful. Well, seeing as we're more than 15 minutes over, thank you for that great answer. And I also want to tell you that there are many comments in the chat, which you can maybe see afterwards. People are saying great talk, very informative. Thank you so much, Alex Petresco and Kyle and others. So I think with that, Gianluigi, it's maybe time for, if you wanted to say any final words before we thank the audience.
Yeah, I don't know. I mean, I might have some postdoc openings. If somebody out there is interested, send me an email.
There you go. All right. It's a great opportunity. I think with that, it's been a real pleasure and treat to have you here, Gianluigi. Thank you, everyone, for tuning in. Thank you, Gianluigi, for accepting the invitation. Hit the subscribe button. And with that, we will see you next week, Friday at 12 p.m. noon Eastern Time on the Qiskit Live Quantum Seminar Series. Enjoy your weekend.